Hello, and welcome to ECE 345. And today we're going to talk about basic signal manipulations and how to do them in MATLAB. So we're going to see what are these basic signal manipulations are. They are the examples of very simple systems that operate on signals, and then get a feel for them by doing it on some audio. That way you'll get a better physical sense of what the systems, what these transformations are actually doing. And that building that kind of intuition about how these systems work is really important for trying to build an understanding of more complicated systems. So our main objectives are to teach how to give the plot of a signal, be able to plot simple manipulations of that signal, including time, various things you can do with the time axis. And then also at the end, we'll do a little bit of frequency domain stuff, high pass and low pass filtering, to kind of get a feel for how that works. And to show some of the issues that arise when you try to deal with things that you think of, say, in continuous time, in a discrete time world that is the computer. The computer is fundamentally operating in a discrete time world. We'd like to show how to do these in MATLAB. And as I said, we're going to work on some audio. So what are these simple signal transformations? Well, the example we're going to run with is in this video is this mystery signal. Now, you can't tell, I'm sure you can't tell what it sounds like. I can't tell what it sounds like looking at it. It's got a bunch of squiggles, right? It's got two channels, left and right. It's a stereo signal, so that's good. Other than that, it looks like it's got some loud bits. The amplitude is a little high, and then it kind of has some smaller bits. It kind of tapers off at the end. But apart from that, I can't really tell that much. I mean, we could zoom in, and I opened this in a program called Audacity, which is an open source program. You can get it yourself, and it allows you to, you can use you can see, maybe you can't see, but there's a little magnifying glass button. You could zoom in, and you could see what the squiggles. This is a very squiggly looking thing. What it looks like. So okay, but what do we want to do to something like this? Suppose this is the data that you've measured on your microphone. Well, the first choice you have when you're sort of thinking about how do you want to set up any kind of signal processing system or that you're going to use, you might be simulating a system to be implemented in hardware later. You have to decide, am I thinking about this as a continuous time signal or as a discrete time signal? Now, as I said before, in the computer, everything is discrete. This thing is stored as like a big array. When I read it into MATLAB, it's going to be a very big, long array, 2 by something, or something by 2. And that's because it's got the 2 channels, and it's got measurements of what? Measurements of the sound pressure wave that have been turned into like some kind of voltage signal and then stored in magnetic memory on the hard drive. So we have so we can model this continuous time, and in continuous time you have this t-axis, which is continuous. So it's you think of it as kind of a curve, and when I say squiggly, so it's squiggling up and down. Or I can think about it as, actually, no, this is really a discrete time signal. I should think about time as an integer. And, I'm going to look at these sort of lollipop-looking stem plots in order to represent this discrete time signal as a discrete time signal. Now, when you're thinking about this, we have to think about what is the context. This is an audio clip. In an audio clip, we think of as being kind of continuous time. That is, we think of the time as being measured in seconds. If I just tell you it's measured in n, it's true. The array might be, 5,000, 20,000 entries long, but what we actually care about is how long is it in seconds. And so therefore, we want to think about this as a continuous time signal when we're thinking about it. But maybe we have to figure out how then to program it to make it look like a continuous time signal in the computer, and sort of respect some of the ways in which we try to represent a continuous time signal as a discrete time signal. So the kind of manipulations we're interested in continuous time are things like delay, so shifting to the graph to the left or to the right, compression or dilation, which is stretching or squishing the time axis, and then time reversal, which is, you could think of it as a special form of dilation. It's flipping the signal, around the vertical axis. So time shifts are the first simplest type of system. It's a delay. It's a delay if it's x minus something is the delay by something. So x minus 10 is a delay by 10, and x plus 10 is a shift to the left by 10. So it's kind of moving it back in time, making it start earlier. And these figures are from this nice book by Ulibi and Yagel, which is posted, it's available for free through the University of Michigan. So in time scaling, what are you doing? You're stretching or squishing the time axis. So remember, we saw before in the equation, mathematically, it's y of t equals x of alpha t. So depending on whether alpha is bigger or smaller than 1, we're going to be stretching or squishing the axis. So how do we remember which way that works? Well, if I make the alpha, the thing multiplying the t, bigger than 1, then it's speeding things up. Time is going alpha times as fast. So if alpha equals 2, like in this plot here, the blue curve turns into the blue triangle turns into the red triangle. The red triangle takes half as long to happen. T is, say, measured in seconds. So whereas the blue triangle took 2 seconds to reach its peak, the red triangle takes 1 second. So it's twice as fast. And the contrary wise is if alpha is less than 1, then it's stretching, it's slowing down time, stretching things out. And so here, if the output is x of t over 2, it takes twice as long. X of t takes 2 seconds to get to its peak, and y2 of t takes 4 seconds to get to its peak. Time reversal, very straightforward. Just look at the axis at time equals 0, and then just mirror image the plot, the graph around it. So graphically, we can see what these 3 things do. And then the question is, can we sort of make that happen computationally? We can see it graphically and we can see it in an equation. But remember, we have these 3 ways of thinking about signals. We have to sort of figure out, can I do it computationally as well? So if we want to put them all together, we can get a sort of general transformation. If we also include, say, a gain, we can also include a gain term a, just multiplying by a constant. And so if we put those things together, we get, x of at minus b. You're going to be stretching or squishing by the factor a. Then you're going to be, delaying by a factor b. And so then the way to think about this is, that you have to there's an order of operations to think about here, right? When I write at minus b, that b is being measured with respect to the time. The way that time is measured in the AT time scale. So you have to be a little bit careful. So what about in discrete time? So this is continuous time, and we're going to be focusing on continuous time a little bit for this audio purposes, but in discrete time, we can also do all sorts of interesting operations. And as I said, the signal that we're going to be putting into the computer is fundamentally also a discrete time signal, right? So these operations also make sense. Well, we can do the same kind of thing. We can delay. We can do something called downsampling, which is to get rid of, to keep only every, 5th sample. So that's what this downsampling does, keep only every 10th sample. So y of 0 equals x of 0, y of 1 equals x of t, and then x of 1 up to x of t minus 1, they get thrown away. So that's what downsampling is. And then we have time reversal. Same thing. We can flip around the 0 time equals 0 point, n equals 0 point. And remember, then the n equals 0 point sample where there is actually a particular value there, that doesn't change. So that's important to consider when we think later on when we're going to be discussing Z transforms. So what about this dilation though? What about like stretching the time axis? Can we stretch the time axis in discrete time? And the answer is yeah, sort of. I mean, downsampling was getting rid or keeping only every, 10th sample, say like every other sample would be t equals 2. We could also do upsampling. Upsampling would be pretend like we only kept every 10th sample of something and then make everything in between 0. So what I'll do is I'll think of like my X signal as like, a deck of cards or something like that, or like a, set of these lollipops, and I'll put the first one at time 0 and the next one at time t and the next one at time 2t and so on. And then in between, I'll just let it be 0. And that's what upsampling is. It's kind of confusing from the formula because like mathematically, it's kind of awkward to write, but it's pretty easy if you look at it graphically. And so I think that's again, thinking about this translation between the math and the graphs and the computation is really helpful to kind of be able to look at all these signals in all these different ways. So if I want to picture downsampling, I'm keeping, say, if I want to keep t equals 2, I'm going to keep, say, only every even sample. So I'll keep n equals, I'll keep x of 0, x of 2, x of 4, and so on. So if I have a signal x of n on the left here, which is alternating in sign, every even time point, it's positive, and every odd point, it's negative, then at the output, I'm going to get only the places where it's even. Positive rather, which is only the even time positions. And so that's we a downsampler by t, or a downsampler by n if we wanted to if we want to use a different letter. So I think really probably this n should probably be a t, or this t, capital T, should be an n, capital N. Similarly, this capital L should be capital T. So an upsampler is spacing out the samples with zeros. So here again, we have our x of n signal. So what do? We take the first element of x of n at times 0, and we stick it at times 0 in the output. Then if t equals 3 here, then we wait 2 stops, so t minus 1 positions. We just kind of put 0, 0, and then we take the next element of x, which is this negative value, and then like around negative 0.5444 or something like that. And then you put the next value of x of n, and then you wait 2, and then you put the next one, and the next 2, and then you wait 2, and put the next one, and so on. So you're just stretching x out, but you're filling in what's in the middle with zeros. So it's kind of like the dilation process that we saw before. The main thing that I want to emphasize is that MATLAB again, I've said it like 3 times now, so I'll say it a 4th time maybe. MATLAB operates in discrete time, always. This is an array. An array is indexed by, integers. So really you should say, oh, everything is a discrete time. But because we're thinking about the audio signal as being a, continuous time phenomenon, we're going to think about frequencies and hertz and stuff like that. We want to be able to translate between this discrete time computational representation and the continuous time, mental representation or in equations and stuff like that. And so the way to do this is to consider the missing element here is what's called the sampling rate. Right, the DT signal comes from a CT signal. It comes from a CT signal, a CT signal sampled at a rate fs. Fs is the sampling frequency. So basically you're saying my discrete time signal is like I take my continuous time signal, I take the curve, and I just grab the value at every t seconds. T is 1 over f of s. So I'm grabbing f of s samples per second, right? And this f of s is giving me the number of integer time steps that correspond to 1 second of actual audio in the real world, real time. So if we keep track of this, we can simulate a continuous time signal because we know essentially how fast to play the discrete time signal, because we know that we should push out of the speaker, fs samples in 1 second. Now, a big warning, and this is a topic that we'll get to at the very end of the class, but we'll try to sort of bring it up in a few times as it comes along, is that if the sampling frequency, fs, is too small, you actually can't capture very high frequencies. And this is kind of intuitive in the sense that if the phenomenon that you're interested in is wiggling too fast, and you are only looking at it pretty slowly, fs is pretty small, you're looking at the sort of capital T is pretty big, then you're going to miss out on all those wiggles. And this is a fundamental issue in signal processing. The rate that you need is something called the Nyquist rate, and the Nyquist rate is related to the maximum frequency in the signal. So we're going to discuss that at the end. But if you ever see in any data sheets or something talking about a Nyquist rate for signals, that's what they mean. They mean talking about how many samples do you need computationally, or in a sampler when you're putting a continuous time phenomenon into a DSP, how fast do you have to grab those samples? All right, so let's get into it. How do you get a clip into MATLAB? Well, there's this nice audio read function. You can take a WAV file, and it outputs 2 things. It outputs a stereo signal and the sampling frequency. The WAV file tells you actually what its sampling rate is. So if I look at the size of this thing, you can see it's almost 300,000 samples, 295 9,936 samples long. And there's 2 channels, and the sampling rate here is 44.1 kilohertz, so 44.1 thousand samples per second. Why is it 44.1 thousand samples per second? Well, because human hearing goes up to about 20,000 hertz, and you need the sampling rate to be twice as big as the maximum frequency. That's the Nyquist rate. So this 44,000 is giving you a little bit of extra room, but it should be able to capture all the phenomena that are within the range of human hearing. At least that's the theory. Now, if you're a big analog electronics analog amplifier audio person, you might say, oh no, it's the digital signals, these MP3s they're just not as good as the old analog stuff. And so I'm not going to debate you about this, but I'm going to say, why did they choose this as an engineering choice? Because this was an engineering choice. They chose this sampling frequency based on human physiology. So we're going to use this sampling rate a lot in the class because it's convenient, and we're going to be doing every time we work with audio, we might as well use it. It's kind of standard for working with audio. All right, so now we have the clip in MATLAB. It's in this this 295,000 or 296,000 by 2 array. So it's 2 big columns, right? And that's the left channel and the right channel. So what we want to do is grab one of those channels, right? So what do? We say, okay, I'm going to set up my time axis. How do I set up a time axis? Well, this is going to be the time axis for continuous time. I'm going to look at all the discrete time samples. There was around 296,000. Capital N was 296,000. So I'm going to take that, and then I'm going to divide by the sampling rate, and that'll tell me that'll 1 over the sampling rate tells me the number of samples per second, and so this will give me the time axis measured in seconds. So now that way, when I plot things, the x-axis will look right. Otherwise, the x-axis would go from 1 to 296,000, and that is hard to interpret because, again, we're working with audio, and we want to understand what does it mean in terms of the properties of the audio, which we think about as a continuous time phenomenon. Okay, so then what do we want to do? Let's visualize it. I mean, I showed it to you in Audacity, but we can also visualize it in MATLAB. And here I'm providing, this is code that I would say is this is a good way to make figures. You want to make sure you have it, if you can, an X label, and I should probably put the units here. I should say time in seconds. Y-axis label, a title for the figure, and then this command will let you print it out to a JPEG, for example, or you can print it out to a PNG. And then if you want to play it, you can play it. This is actually should be the X sound SC of X, not XREV of FS, and you have to give it the sampling rate because you have to tell it how fast to play the audio, right? How fast to play this discrete array. So if we plot it, we get something looks a little squished version of the one that we saw from before in Audacity, but more or less the same. Still pretty hard to tell what's going on here. But you can see here the time is measured in seconds. It's about 4 and 4¼ seconds long. So if we wanted to reverse the sample, how do we do it? Well, one channel is, remember, it's a big long array. It's many rows in one column. So there's this nice command, actually, flip UD, flip up to down. There's also flip LR from flip left to right, and that'll just flip the array upside down, which is a handy little function. And so we can also plot that. So let's plot that. So this is the time reversed version of the signal, that is, I've kind of reversed it in time. So here it is, and so not sure if you can tell what that is, but maybe it should be familiar if you play it the right way around. We don't talk about Bruno. So pretty familiar clip, hopefully, unless you've been unaware of many things in the last year. So this is a clip from the movie Encanto, the song "We Don't Talk About Bruno." And we played the reversed version, and then we played the original version. So you can sort of hear what's going on in the reverse version. It's got this kind of like, sounds a bit like a sucking sound, like a, you know, kind of like, because, and that's because the audio, it's the air is kind of moving forward and you're kind of playing in reverse. So you're really kind of, it's got this sucking in quality about it. And you can see that also when you watch, if you watch reversed videos, when people like in some sort of TV show, you know, they're like, oh, something rolls back in time. You can see kind of the way, because of the way the physics is like working backwards. You get this kind of, you get a visual sense of it. So this is the audio sense of that kind of reversal. Okay, so what do we do? What are our other signal manipulations? We can delay things, and so we can do some time shifts. How do we do a time shift? It's a little more complicated because I've read it in as just as an array. So basically, we have to stick in some zeros at the beginning, and there's the code to stick in a number of zeros. You need to figure out, if I want to delay by 3 seconds, then I have to create an array of zeros that is 3 seconds long, and 3 seconds long is going to be you know, some number of, you know, 3 seconds times fs, the sampling rate. That's how many samples you're going to need to put in. And so then we can plot that, and we can also play that. So let's play it now. At least I hope it'll work. Oop. It's a little tricky for me because somehow the icon of exactly where the play button seems to have vanished in the Zoom recording here. So if we wanted to speed things up, well, what do we do then? Well, it's a little bit it's not that complicated. We have to figure out what is the length of the new signal that's speeded up. When we want to speed things up, remember, we want to kind of keep only every other sample. So this is going to be like a downsampling operation. So there are some functions which will just downsample a signal in MATLAB for you. Here I'm just doing it kind of in a gory brute force sort of way. And here what I'm doing is I'm essentially keeping only the every other of the even numbered samples. That's what the 2 inside the x full is. X full is the whole clip, is the original clip, and then I'm keeping only the even samples. Then of course we can do this and we can plot it. So if we speed it up, it should just look like it's squished, right? And it looks squished because before it was 4¼ seconds long, and now it's you know, now it's like 2 and some change long. So that was quite something. Let's hear it again. Oop. So you can see twice as fast is actually really fast. It really sounds like everything is like very high, tinny, sounds like chipmunks. But that's what happens when you play something fast. Now you could play around with this code. You could play it at, you know, 1.2x speed. Perhaps you think that I'm talking too fast in this video, and maybe you're playing it on YouTube at 1.x speed, and so at 1.5x speed. And so what they do, when you notice, if you do that, if you take this video and you start playing it at 1.5x, why doesn't it sound like this? If you played at 2x, it won't sound, I won't start sounding like a chipmunk. I won't sound like that, right? Why won't I sound like that? And it's because they do some post-processing, right? When I throw away those samples, I'm playing it at the same speed with that same sampling rate fs. If I took this and played it as using a lower sampling rate, because now instead of fs, I have fs over 2 samples per second, it should sound, well, normal, not completely normal, but at least you know, not quite as terrible. It will still sound not so great. And so I recommend trying it out. Try doing the audio play, but with a different choice of fs, and you can see how that works. So if I wanted to slow things down, I have 2 choices. I can treat it as a DT signal, in which case I can just put zeros in, or I can do what's called linear interpolation, which means what I'll do is I will you know, if these are my two samples in my array, and I'm now spaced them one apart, and say there would be a 0 in the after the upsample, there'd be a 0 in the middle. I'll just draw a line and put a sample in that's kind of a line between them. That's what's called linear interpolation. You're just basically connecting the dots in the discrete time signal. So here's some code to do that. And if you do that, you know, it should sound quite a bit slower. And so let's see what it looks like. Indeed, it was 4 and change seconds long. Now it's like 8 and change seconds long, and it will sound pretty languid. Now, I have been listening to this clip over and over and over again, making these slides. So now it sounds quite, you know, I can tell what they're saying. But maybe if you just played it once for you, you're having a little bit of a hard time. I know the first time I played it, I said, oh, I have no idea what's going on here. But you can hear what's happened here is now, because you've stretched things out, but you're still playing it at the same sampling rate, fs, all of the frequencies become twice as slow. So everything becomes lower. So that's why you get this kind of lower kind of distorted sound, because you're basically playing everything half as fast, right? And this is what that does in terms of the audio, right? So again, we're trying to get a physical interpretation or physical feeling for what happens when you do various manipulations to your signal. That's the point of that we're trying to get across here. But maybe we want to do something more simple than just kind of shifting things around and speeding them up and slowing them down. Like, what if I, you know, wanted to do something like, you know, keep only the bass part, or keep only the treble part, or something like that. Keep the high part and the low part, or I want to change around the mix of things. You can do that, and you can do that with using different tools. Also, we can do in MATLAB. So remember, systems are things that transform signals. Right now, we've been kind of, you know, we've been transforming signals, but we've been doing it in a kind of like a simple way, right? A very simple way. And so if we want to design signals like a stereo equalizer, we need to be able to do more complicated things than just shift signals around and flip them upside down or flip them around and stuff like that. So what is that? So a big moral of the story for this class is that when we focus on linear time invariant systems, we can think about what they're doing to signals in terms of how they're affecting different frequency components in the signal. Right? So we should think about the signals as maybe made up of different amounts of stuff at different frequencies, different kind of like energy at different frequencies, and that what the system is doing is it's pushing some up and pulling some down. And so what is happening here is we're saying that signals can be approximated by essentially linear combinations of sinusoids at different frequencies, and systems are manipulating those the weights, the coefficients in that linear combination to produce the output signal. So one important example are something called bandpass filters. Bandpass filters means it passes the signal, that is, the signal goes through kind of undistorted in a as long as all the frequency components in a certain frequency range. So like maybe 440 hertz to 880 hertz or something like that. Then you're keeping only that octave between 440 hertz and 880 hertz. And then all the other frequencies outside that, higher and lower, all the content in the signal at those frequencies should get pushed down. So you know, special cases of bandpass filters are high pass filters, which say everything above a certain frequency gets cut off, you know, gets kind of tamped down, and that's right, everything below a certain frequency gets tamped down, and keeps high pass means you keep only the high part of the signal, and low pass means you keep only the low part of the signal. So you after a certain frequency, you cut off the rest of it. And we're going to be looking at high pass and low pass filters later in the course, but we should at least know what they are now. This is what they do. This is what we mean when we talk about high pass and low pass filters. And these filters are used like everywhere. They're used in your phone, they're used in your stereo, they're used in your ear even. There is physiological modeling of the human ear, which suggests that the neurons in the human cochlea are essentially doing bandpass filtering at different frequency bands, and that's how the brain is processing information that's coming into the ears. So in MATLAB, there's a bandpass function. and it says filter signals with a bandpass filter. And so if you look at the documentation for this function, it filters the input x, y equals bandpass of x, and w pass. W is, I guess, omega. Filters an input x with a bandpass filter that has a pass band frequency range. So pass band frequency range means the frequencies that can get through and that are not blocked by the filter, defined by the two-element vector w pass, which is lower and upper. And the elements of w pass are given in normalized units of pi times radians per sample, and its values must be within the 0-1 interval. Well, that's confusing because we were dealing with like hertz before, and that's because this is representing the signal and representing the filter as a discrete time operation. And in discrete time, our frequencies are not going to be. We don't have a notion of hertz because we don't have a notion of seconds. So this seems like it's not. You're like, oh, this might not be the function I want. But if you scroll a little bit down, you'll see, oh, there's actually a different way of using the bandpass function. You can give it fpass and fs, where now you say fpass is a two-element array with a lower and upper bound. And those define the range of the filter in units of hertz. But why couldn't we do that before? Because here we also have to tell you the sampling rate, fs. And so everything in this continuous time simulation, or sorry, discrete time simulation of a continuous time system, everything is predicated on there being this special sampling rate fs that is the gateway to allow you to translate indices into an array into seconds in time. And so you can represent your thing as frequencies in hertz if you also tell me tell MATLAB the sampling rate. And then once you're there, it will do the translation and create the correct filtering operation for you. Bandpass is a general function. There's special functions which work actually a little bit better, I think, called low pass and high pass. And low pass and high pass work very similarly. So the low pass function, if you do help low pass, you'll get this. Has the same kind of usage. You can also call it with a passband frequency fs. Now here it's just one element. It tells you low pass says keep everything up to, pass everything below this particular frequency fpass, and then everything above fpass, attenuate it. And of course, you can't do a perfect filter in reality, but this is that is, you can't have a perfectly sharp cutoff. But this is the design goal is to make the cutoff at fpass. And high pass is the same way, except it's now saying, give me a frequency fpass, keep everything that's got a higher frequency in the signal, higher frequency components in the signal above that, and then the lower ones, please, push those down. So if I want to get the treble, I'll use high pass, and if I want to get the bass, I'm going to use low pass. So here's how you do it in MATLAB. I can establish, say, a low pass filter with at 440 hertz, and then I could do a high pass filter at 1 kilohertz, for example. And so we can take a listen to see what that sounds like, right? So again, the high pass filter is keeping only the higher frequencies. So you can tell it sounds a little tinny, right? This is what happens when you block out the low frequencies. So keeping only their high pass, you're keeping only the high frequencies. So it sounds little tinny, like a bad radio, a bad speaker, right? Bad speaker system. If you keep only the lower frequencies, then you're going to get rid of some of that treble effect, and you're going to get something quite different. So it sounds a little bit like it's like underwater or something like that, I think. And so I think this is the, again, you're trying to build a physical sense of how these different filters work and what it's doing to the system, and what it's doing, sorry, to the signals, what the system, these filters are doing to the signals. And so I encourage you to play around with this code and try it on your, clips that you like and see what it does to them. And you got to build yourself that physical intuition for what these systems are doing. So just to recap, reading audio data into MATLAB and then performing simple manipulations is not too hard. You just have to be a little bit careful, and you have to have a good sense of how to translate the visual thing into the code. And we can get a feel for what these signals transformations do by listening to their effect on the audio. And we can also see what they do by looking at it graphically. But we can do equations and graphs, on our own. That is without a computer assistance. The nice thing about having the computer there is that it gives us an opportunity to kind of have an experiential feeling of what these systems are doing. And we can do more complex manipulations on the frequency content, but we have to do so, we have to make sure we're paying attention to the sampling rate. That is, we need to always take into account the fact that we are simulating a continuous time phenomenon in a discrete time computational world. And that key between the two is the sampling rate, Fs. And so I encourage you again to kind of take some of these things or play around with the audio yourself and see what you can come up with. See if you can come up with a really cool effect, just with these simple transformations. Thanks so much, and we'll hopefully get some more MATLAB maybe later in these presentations.